Hi everyone. Today I'm here to present our final software tools project. Our project name is Face Generative Model, and here are our group members. And the next slide is the overview of the project. So the main goal of the project is to be train an AI image into a realistic image of a human faces based on a facial expressions. So for this project we use like 6 dataset, like angry, happy, neutral, sad, surprise. So we have done both generator and discriminator. So here the generator. So the generator creates a fake image from real image, and the discriminator will create and generate image and the original image. So here are the few observations which will um, be explained later. So here's the next slide. So this slide, this so that this code explain the zipped file folder from a Google Drive and download it in a collab folder. This is the coding for the downloading and downloading it in collab folder. And here is the this code explains the some variables needed for training a neural network using PyTorch. Here we use the G losses and D losses for storing the losses of the generator and discriminator during the training. The next slide, here we mention the file path, batch size, number of epochs to train the model. So further we use the NGF and NGF. These are all the feature maps, and it determines the depth of the generator and discriminator network. And the next slide, the custom dataset class. It will create a custom dataset for training, inheriting from PyTorch. Here is the name of the file, and it reads data for CSV file, load corresponding images, and further for data transformation. And there's the continuation, like the transformation, and it will create a custom data set and then create the data loader, and that it will run. And the next slide, this explains the transformation pipeline using transforms.compose. We use transform.compose for the transformation pipelines, which will resize the image to which will resize the image of 64 pixels. We just resized all the images into the size into the same size of 64 pixels, and it converts into a PyTorch sensor. And the next slide, this is the images, which will is the neutral, sad, surprise, happy, and angry. These are all the images we have uh, given. These are all the AI images, which will convert into real images. So the next slide, those two snippets define the architecture of the generator network, which takes random noise as input, and the generated fake image, which will generate a fake images. So here are this is the code for fake image, and this is the continuation. This is the generator which we created, and this is the discriminator classes. This code explains the discriminator class construct a neural network of comprising convolutional layer, batch normalization, and leaky or ReLU activation. So which will distinguish the real and the fake image. This code is used to distinguish between the real and the fake image. And here is this will create a discriminator to differentiate. And this code is the continuation of the discriminator. Here we got the discriminator which we already did.
Thank you, Swetha. So moving to the next slide, this piece of code configures the optimizers and loss function for the generative adversarial network, which is GAN training process. It also defines certain other variables and parameters that are required for the training processes. Going to the next slide. Here we have fed around like 50 epochs. In first uses it first uses a real photos to train the discriminator, then it uses a generator to create the false images, then the generator is trained after the discriminator has been updated, and it computes the generator's loss and uses the generator to produce phony images. And in order to facilitate future charting, it appends the discriminator and generator losses to the corresponding lists, which is D losses and G losses. Moving to the next slide. Yeah, this code is the continuation of the previous one. Next one. Yeah, this is the output that we have had for the 50 epochs. As you can see, there is loss D and loss G in it. The loss D is the discriminator loss and the G is generator loss. Next slide. Okay, using torch.save, the generator and the discriminator model state discriminaries are preserved. The models and for the generator and discriminator are saved in the files called generator.pth and the discriminator.pth respectively, as you can see in the code. Moving to the next slide. The code sample below uses an API token for authentication when it creates a repository on the Hugging Face hub and uploads a given model file to it. Hmm. Next one, 19th slide. This feature makes it possible to see the variety of images that are generated across several classes, which sheds light on the caliber and variety of the generated samples that the GAN produces. Moving to the next slide. Since we have trained the model for 50 epochs, the generated image was like this. It was not clear, it was not proper. Why? Because for 50 epochs, it took around 2 hours and the session got crashed. So we um, try to run in CPU and not in GPU, which was better. And this piece of code defines the function compare underscore image, which contrasts generator images from the trained GAN generator, which original images from the dataset. To modify the layout, it uses plt.height underscore layout. To compare the original and created photos, it uses plt.show. You can check in the code, you'll get it. Moving to the next slide. Yeah, here this is nothing but we have compared between original images and the generated image. The first row is fully original and the second row is fully generated. As you can see, the first row is pretty clear compared to the generated one. Next slide. Okay, this graphic illustrates the evaluation of the generator and discriminator losses over the training iterations, providing a visual representation for the training process, and it aids in evaluating the GAN's convergence and stability throughout the training. Here we have the last slide. This code allows the checkpoints dictionary to be downloaded as a zip file, which the code has been saved for every 5 minutes. Thank you so much.